So that's coming to the next portion. Force exerted on a series of radially curved vanes and hitting tangentially on the curve. We have just earlier seen that we have a single vane. The vane was moving with the velocity, but here what we have, we're having a series of vanes like this. And if the water is hitting here, the water is hitting this vane with a velocity here. The absolute velocity, let it be v1. So this will be moving in this direction, this will be rotating. When it hits, it will be having a rotation, so this will be moving like this. So once it hits, the vane is not stationary, it will be having quite a angular velocity. It will be keeping on moving. So it will be having the inlet. The inlet, what happens is, the velocity is u1, the vane velocity is u1. So the relative velocity with which it is going inside will be vr. Similarly, it will be coming out. So this is how it is getting rotated. These are the vanes, and here you have kept a series of vanes. So I'll be just taking a few. I'll be just cutting this and showing this in a magnified view. So this is your single jet, and this was your absolute velocity that was hitting the vane. This is v1, and at this inlet you have a tangential. This is your tangential velocity. And here your tangent is going like this, that's your tangent. So here you will be having a tangential velocity that is u1. So you have a resultant velocity vr1. We have discussed all these things, and it will be coming out with a velocity of, we know that it will be coming out with a velocity of vr2. And at this portion it will be having a tangential velocity of u2. So that's why it will be the absolute velocity is v2 here. This all thing you know it. Now I'll be drawing a line which is parallel to this tangent. This angle, the absolute velocity is making an angle alpha, and relative velocity is making an angle theta. Similarly, I'll be extending this parallel to this tangent. This relative velocity is making an angle phi, while the absolute velocity is making an angle beta with that line. So these are the angles, and this is how it is working. Now I've always said we'll be always resolving the actual velocity. v1 being resolved, we'll be getting this as vf1 and this is vw1. Similarly, if I am resolving the absolute velocity v2, this is vw2 and this is vf2. These are the things that we are going to get. Now I've already said earlier we have derived the equation for this when this was moving, but it was not a series of planes. As this goes, the other thing comes. That's why it's called as a series of radially curved vanes. Before that, what we have seen in the previous video, what we have derived the equation for the force was, force in x direction was equal to rho into q into vw1 plus or minus vw2 was the equation. And since there in that equation what happened, it was not a series of vanes but it was just moving, so that's why we have written the equation rho into a into vr1 into vw1 plus or minus vw2. This was the equation which we have derived already. But here what happens is, I've already said that when you have a series of jet going like this, you have to substitute discharge is equal to area multiplied by the actual velocity. Here the jet, the absolute or actual velocity is v1, so you have to substitute v1. So that's why this equation gets modified as fx is equal to rho into a into v1 into vw1 plus or minus vw2. So that will be the equation for your force, no doubt for that. So this is the equation that you'll get. Rho fx is equal to rho a v1 into vw1 plus or minus vw2. This is the most general equation. That means when this angle beta is less than 90 degree, you can write fx is equal to rho a v1 into vw1 plus vw2. This was the equation when it was acute. But at the same time, when beta is more than 90 degree, fx is equal to rho a v1 into vw1 minus vw2. This is the equation that you have. And when third one, when beta is equal to 90 degree, this is perfectly 90 degree, you won't be having that vw2, so you can write fx is equal to rho a v1 multiplied by VW1. These are the different forms of equation, and this is the most general equation that you will be writing. So we know that the force is equal to the rate of change of momentum, the rate of change of momentum. So I can say that the force in x direction is equal to initial rate of momentum in x direction minus final rate of momentum in x direction, because this is the difference, or rather the rate of change of momentum. It's initial rate of momentum in x direction minus final rate of momentum in x direction. I'm just taking this condition because we have all drawn the figure with respect to beta is less than 90 degrees, so I'll be using this equation. That means that if I substitute that, I can say that rho into A into V1 into VW1 is the initial rate of momentum in x direction. And if I multiply, that has to be minus of minus rho into A into V1 into VW2. And with this both negative becomes plus, then only you will be getting this equation. So this is your initial rate of momentum, and this minus rho A V1 VW2 is your final rate of momentum. Now I need to calculate the force, that is work done by this thing, the work done on this. You know that the work done is equal to work done per unit time. You have already seen that is nothing but force multiplied by velocity, that v. Then I need to find the work done in x direction. Work done per unit time or unit second in x direction is equal to force in x direction multiplied by velocity in x direction, that is u. But the problem with is that at the inlet you are having a velocity u1, at the outlet you are having a velocity u2. Earlier in the previous case we have assumed it to be u1 and u2 are same, but in this case both will not be same, because what happens is it is rotating in a wheel like this. So the inner velocity will not be same as that of the outer velocity. See, what happens is this whole thing will be rotating like this. Though it is having the same angular velocity, the tangential velocity will not be same. This will be moving with one velocity, this will be moving with another velocity. Similarly, this is u1, this is u2, both will not be same. So I cannot say that both are same. So what happens at the outlet, at the inlet point? At the inlet point I need to find the work done. So work done per unit time in x direction corresponding to inlet. At the inlet, what can I say, that it will be equal to fx multiplied by the tangential velocity of the inlet, that is u1. That can be written as the force we know, that is this one, the force at the inlet, that is rho into A into V1 into W. That's the initial portion is the inlet portion. So this is the initial force, that is initial rate of change of moment. Let's go into A into V1 into VW1 multiplied by U1. Similarly, I can say that the work done per second in x direction at the outlet will be equal to force in x multiplied by the outlet velocity, that is u2. So that can be written as rho into A into V1 into VW2 multiplied by u. But see, there's a negative sign. So this is the work done. So one is going in this way. Here the work done. This work done. We have in fact, the force is a scale, a vector quantity. This work done does not have any meaning. Work done we cannot write positive or negative. Work done will be always positive. So the total work done per second, I can write it as rho A V1 VW1 into U1 plus rho into A V1 VW2 into U2. All these terms, the first two, the row A V1 is common, so I can row A V1 multiplied by VW1 U1 plus VW2 U2. So this is the total work done when you have a moving curved vane, but it is in a wheel or a series of vanes, and one after the other different veins are coming. When all are coming together, it's not an individual or single vein, you have a series of veins. So this is the equation to find the work done. So then the most general equation, so this was, that equation was valid, that equation which we have written, the work done, which is equal to rho into A V1 into VW1 U1 plus VW2 U2 is applicable when your beta is less than 90 degree. When your beta is more than 90 degree, what happens is the work done will be equal to rho A V1 into VW1 U1 minus VW U2. So in general equation I can write the work done is equal to rho A into V1 VW1 U1 plus or minus VW2 U2. This is the most general equation that you can have for the work done. At the same time, the initial kinetic energy per unit time, we have already derived this equation. It is nothing but half into rho into A. We just derive once again half into m v square by time, and mass is density into volume multiplied by v square by t. Now here, what is the velocity? Initial velocity what will be considered, because the jet was coming. See, the jet was there, it was giving out velocity. The initial velocity with which it is coming out is v1. The velocity with which it is coming out is v1 there. So that has to be v1 square. So equal to this volume by time will be discharge. So half into rho into discharge into v1 square. Now I need to calculate the discharge. Here, what type of thing you have? You have a vane which is not stationary, which is moving, but it is not a single vane. You have a series of vanes. So when you have a series of vanes, you have to substitute that as a into v itself. Here the initial velocity is v1, so it can be written as half into rho into area. Area is small, a into v1. So that is for discharge multiplied by v1 square. So that is half rho a v1 cube. So that makes the efficiency, the output power. Output power is this much, rho a v1 into vw1 u1 plus or minus vw2 u2, the whole divided by half into rho into a v1 cube. So if you cancel out, you will be getting that is equal to 2 times vw1 u1 plus or minus vw2 u2, the whole divided by v1 square. So this is your equation for efficiency when you are having a series of curved vanes. This is the equation for your efficiency.